Okay, guys, today we are going again to the chapter 10, reading medical physics for physics science students about electricity. Yes, electric charge, conductors, semiconductors. We have talked a system or a physical field. Yes, the particle of zero size carries an electric charge. Yes, uh, we are trying to explain the electrical behavior of the electron and protons, as well as describe it by modeling them as a point charge. Yes, the force is attractive if the charge are of opposite sign. The force is repulsive if the charge are of like sign. Yes. Yeah, when we're talking about the quantization charges, yes, that the electric charge is said to be quantized. So we have in the seed unit we have the unit of charge is a coulomb, yes, and it means the electric charge exists as gets, yes. The elemental fundamental unit of the charge of electron. It's a minus 1.6 multiplying on 10 in the power of minus 19 coulomb. Yes, this is an elementary fundamental unit of charge. Electrical force, point charges, is given, yes, mathematically, where the force between 2 points charges are equals to the proportionality Coulomb constant, yes, it's a 1 divided on 4 p epsilon 0, yes, multiplying on the this product, so it's proportional to equality to amount of the charge multiplying to a second amount, yes, and reversely proportionally to the square two charges, yes. This distance in denominator with the in the power, the very noticeable law of dependence between the force and the electric field and distance. Again, we have met the same law when we gravitational forces. Yes, we have nearly the same. So we have in electricity, we have the planet, yes, Coulomb take the gravitational basement of the Newton, and he have take the gravitational model of explaining electrical force, yes, to taking the explanation the gravitational force of planetary. We have the same coefficient of proportionality here, but here is that it's Coulomb's law of gravitational gravity big, and the amount of mass, yes, mass of the first planet here and mass of the second planet here, they are them, and they're dividing on their squared distance between them. Here, yes, the electrical force is reversely proportional to the squared distance between them. Yes, again, electric field is said that exists in the region around a charged object. Yes, and the charged object is the source charge. So we take another object, charged object, the third charge enters this electric force acts on it. Yes, the electric field vector E At a point in space, its electric force acting on a positive test charge placed at that point divided by the test charge. C units of electric field vector is Newton per Coulomb. Yes, and their formula analytically. We wrote this explanation, this definition like Fe of electric field divided on Q. Yes, it will be Ke, coefficient of electricity, Coulomb constant, multiplying on Q divided on the square and on the radius vector. Yes. Again, electric field line. The spatial type of the lines of electric field to explain how it's distributed in the space around the charge, yes? And the magnitude of the field is greater, the greater is this magnitude of electric field in that region. So the number of light area through a surface perpendicular is proportional to the magnitude of electric field in this region. For the point charge, the field lines are directed away negative, they are directed direct charge in all directions. We'll talk about the dipole, that we have two charges in them, and this dipole of two charge with the opposite sign. Here, this charge are equal of field lines, leaving the dominating on the negative charge. About the electrical dipole, use the electrical potential energy. Repeated the our potential energy, or movement of the charge from point A to B. The work is done by the field is the charge potential energy delta U. Yes, it's UB QA. Yes, and to define definition of electric potential. Yes, energy per unit of the charge is the electric potential. Electric potential V, yes, it's U divided on Q0. Yes, the potential is a scalar quantity because the energy is scalar. So 1 volt. So 1 volt, it's 1 joule divided on coulomb. Yes, 1 coulomb. So, and in another definition, in addition, we 1 Newton per coulomb, it's 1 volt per meter. Yes. So, potential difference between 2 points N and B be simplified as a field is uniform. So your delta V, yes, minus ED. Yes, the electrical vector on the distance between 2 points. Then potential due to a point charge at some point R will be the coefficient of proportionality multiplied on this ratio between the Q charge and the distance from the. And this analytical formula of electric potential due to several points, yes, you have this. So the task I have give you, yes, and yes, they are devices that store electric charge, yes. Different type of the examples where the capacitors are used include their radio receivers, filter in power they're using to eliminate sparkling in automobile ignition system, and they're using in energy storing devices in electronic flashes. Yes, we have two conductors, two plates. Yes, from conductor and discharge, the plates carry out charge of equal magnitude and opposite direction. Potential difference exists between the plates due to the charge. Yes, the definition of capacitance. The capacitance of the capacitors here is defined as the ratio of the magnitude of the charge on either conductor to the potential conductors. Yes, the capacitance of a given capacitors is constant. It's a feature of this capacitor, this exact capacitor. The capacitors, yes, unit of them. The farad is very large. Typically, you will see microfarad, MF, and picofarad. Yes, here is not a milli, it's a microfarad. Yes, the formula of the capacitance for the parallel capacitor divided on delta V. Yes, the end result will be epsilon 0 multiplier of the each plate. The area of each plate is equal, and the Q on each plate equal with opposite signs. Yes, D is a distance here between plates of metal. Yeah, and they're joined to some accumulator. Yes, and the charge on its plate. So then we take the dielectric capacitors. It increases the capacity of the capacitor here. When we in material, then we put the plates of the capacitors. Yes, it is and increase the maximum operating voltage. Glass and even waxed paper. Yes. So task previous time was solved. Example of the capacitors, different type of the live capacitors, yes, about myelinated and non-myelinated axon, yes. So tables of dielectric constants and dielectric strengths. Yes, previous time I was talking about them, and we need to go in electric current. Yes. So the most practical application of electricity deal with the electric currents. Yes, we need to talking about that some electric charges will move through some region of the space. Yes, the electric current is the flow of charge through some region of space. Yes, the direction of the current in which positive charge are free to do so. Yes, so he was made historically. Yes, the movement of the positive charges free to do so. Yes, so electric current is the rate of flow of charge through some region of space, through of some conductor, for example, some area. Yes. Assume charges that are moving over area A, and if you had exactly passes through this A, the cross area A in the time, then the average current will be the average current is the ratio between this delta Q divided on delta T. Symbol for electric current is I. And the direction of the current flow is the direction of the flow of electrons. It's common to refer to any moving charge as a charge carrier. Yes, this special type of the electric current is the unit of C system, international unit system. It's ampere. Actually, it's a big current. Yes, 1 ampere. It's 1 coulomb per second. Yes. And we go into Ohm's law, the most biggest law of electricity, the most a very very famous law of electricity, because many tasks are standing on this law. Mathematically, the voltage on the this type of the current V is equal to this current, yes, current force, multiplying on the resistance of this part of the circuit, yes, of this type of the space. Materials that obey Ohm's law are said to be ohmic. Most metals obey Ohm's law. Yes, most of them. They are ohmic. Materials that not obey Ohm's law are said to be non-ohmic. Yes, and actually when we put this dependence of the voltage, current voltage, volt ampere characteristics, yes, of the some spatial value of the, we receive this slope. Mathematically, it's linear dependence with the Ohm's law, yes? And the slope will be equal to 1 divided on R, the resistance. Resistance here is the R equals to rho multiplying on L divided on A, whereas the rho is the resistivity, yes? The spatial type of the resistivity of material. So every ohmic material has the characteristic resistivity that actually depends on the properties of the material, and they have the dependence from temperature inside it, yes, of the material. So the characteristic of the body of the ohmic material is their resistivity, yes. The resistance of material depends on its geometry and resistivity. And here is the formula. L, it's the length of the conductor, and the divided on A, the area of the conductor, yes, the cross area of the conductor. So the C unit of resistance will be ohms, ohm. It's a 1 volt divided on 1 ampere. Yes, it's the unit of the dimensions of this special type of value, resistance. The circuit arises due to collisions between the electrons carrying the current with the fixed atoms inside the conductor. The most electric circuit use circuit elements called resistors to control the current in the various parts of the circuit. Yes. Example: exoplasm resistance. The electrical resistance R along the length of the axon follows the same principles as a wire. Yes. The R is equal to rho axon multiplying on L, the length of the axon, divided on P squared. Here is the cross area of the axon. Yes. For the both myelinated and unmyelinated neurons, the resistivity rho A for the exoplasm is 2.0 ohm multiply meter. Yes. So the average neuron, it has an axon a meter long, yes, and the 5 micrometer radius. We can find that the resistance of the exoplasm, R exoplasm, yes, from that formula. When we put inside the numerical values, yes, R squared, it's your 5 micrometer, yes, squared, and the longs, it will be 1 millimeter. But not forget to turn off the this spatial type of unit, millimeter and micrometer. we need to turn it to the unit of international system unit, to the meter. Yes, and we will receive, after all mathematical transformations, we will receive 2.5 multiplying on 10 in the power of 7 ohm. Yes, it's a big resistance actually. This huge value indicates that axons are actually poor electrical conductors. Yes, it's a bad conductors. So we need to go to resistors. I can look to the... Goodbye everybody. We have some people who are listening to this lecture. Okay, everybody welcome. Yeah, and we are going more. Yes, we need resistors could be in series and in parallel connections. Yes, when we have these resistors here on the left, on the picture A and B here, we have this series, first one on the right hand of me, in the upper part of the presentation, for the series of combinations of resistors that are have the one near each other, series. Yes, the current are the same in all the resistance. So the current are going from the source of the current, from the accumulator, for example. Yes, the circuit diagram here, yes, some simple primitive diagram of the circuit that's showing the two resistors connected in series to some battery, to the source of the current. The current gives us some delta V, the difference of potentials, and they give us the I. Yes, and the I are going through these resistors N1 and R2. Yes, the current will be the same. I is equally to I1 on the first resistor and I2 on the second resistor. But the equivalent resistance here has the same effect on the surface, yes, and the original is the combinations of the resistors. So the something like equivalent resistance here of this part of the circuit, whereas you have your series combinations of resistors, it will be the sum of resistance on this part of the it will be equivalent resistance will be the R1 plus S plus R2 plus R3 plus how much there in this circuit on this part of the circuit. Yes, so there will be original combination of the resistors, but in combinations of resistors, the potential difference across each resistor here you can look at my right hand of this presentation. Here the circuit diagram showing the two resistors connected in parallel to a battery here. Yes, we have the potential difference across each resistor is the same because each is connected directly across the battery terminals. Yes, delta V is equal to delta V1 equal to delta V2 here. The potential difference across each resistor is... Yes, in the first part, when we have series of combination of resistors, we have the sum of the delta V of the old circuit will give us the sum of delta V1 plus delta V2. But on this circuit diagram showing us two resistors connected in parallel to the battery, to the accumulator or source or the current will give us the parallel combination of resistance, the potential difference a resistor is the same because each is connecting directly across the battery terminal. It's something like they are standing in the same points. Between them we have this difference of potential. That's why they receive the same delta V. The same difference between these 2 points, A and B. Yes? And we have the same potential difference. So delta V on 1 delta equals to delta V2 and equals delta V in all system, delta V of accumulators, because the difference of potential between 2 points A and B. The equivalent resistance in this type of the circuit, parallel combination of resistors, will give us the 1 divided on resistance equal, yes, will give you the sum of this ratio, yes, 1 divided on R1 plus 1 divided on R2 plus how much them in this circuit. This is the formula of equivalent resistance, yes, reverse dependence, the dependence of ratios. Okay, we are going to electric power, and here is that on the picture we can look at the special type our join our electrical system when we use it in everyday life, because your electricity current that you use in this class, yes, for the electronically internet system to have distance learning, this current is not born inside your electrical distributing system on the exit of your room, yes, it made on the factory, yes, on the generator of the factory or the electricity on the something like atomic generator, yes, the atom electric station or the thermoelectric station, yes, or hydroelectric station. Here is the on the picture we have some special line of linear of electronic transform here with a huge voltage, yes, and the power of current to transform this electricity with little losses for the huge distances, yes, special type of the lines of transformation of electronic energy, of electricity lines here. Yes, we need to talk about electric power, what we're using in everyday life. The power is the rate at which the energy is delivered to resistor. Yes, actually it's the definition, and the power is given by the equation P. Yes, it's equal to the current multiplying on this difference of potential, yes, or the voltage on this part of the circuit between 2 points, yes, this difference of potential or the voltage inside the this part of the circle. We need to apply the Ohm's law. The alternative expression of the Ohm's law can be found using the this special type of the equation. P is E multiplying on delta V, yes, the current multiplying on difference of potentials, yes, it's the difference of potentials. It will be your product of current and resistance on this part of the circuit, and it will be the result will be the E squared, yes, because I multiplying on I, yes, and multiplying on the resistance. So the current squared multiplying on resistance. It's another expression for the finding power, electric power in the rate of the energy which is delivered to the resistor. Yes, and we also could write in another way. When we put inside the I, yes, we can express the I, the current on the part of the circuit, like the ratio of the delta V divided on R. So the difference of potential divided on resistance on this part of the circuit. It will be delta V, result will be squared because delta V multiplying on delta V, yes, here. And we divided resistance, yes, it's the both three-way alternative expressions can be found from the applying Ohm's law. Don't forget that unit of the current is the ampere, unit of the resistance is in ohm, unit of the differential is volt, yes, and the power will be watt, yes, and you use this power, and every label of some electricity device could include the explanation what the power, what's electrical power of your device is. Yes, it's something like feature of the device, of the equipment. Yes. The example of power is an electric heater. Yes, electric heater is constructed by applying a potential difference of one American system, yes, American system of electricity distribution. They have the 120 volts. Yes, we have here in this country 220 volt inside the electrical system. Yes. We have another way of explanation what voltage inside our electrical distribution system. Yes, but here in this task we are using this type of the American electronic system, and we use 120 volt, yes, to a nichrome wire. We have special what we have in the electric heater. What is the construction? It's a nichrome wire, yes, to make a solenoid. Yes, we have some spring, very huge, rather big spring, yes, with many these wheels of the these rounds of the nichrome wire, solenoid, or something like spring, made from nichrome, that is joined to the potential difference of our electrical system, to the circuit. Yes, so we are applying here the potential difference of the 120 volt to the nichrome wire that has actually a total resistance of 8 ohm. Yes, big resistance actually, and it begins to be heating, yes, by electrical acting on it. Yes, by this, because it's big resistance, we are starting to take this active thermal energy, yes, from it. So we need to find the current carried by the wire and the power rating of the heater. Actually, what we're trying to use this thermal energy what we receive due to the big resistance of nichrome wire to the electrical energy, yes, electrical current going through it, yes, because potential difference of 120 volts, use it, apply it to this nichrome wire, yes. And the solution of this task will be that because we have this difference of potential, yes, and it equals from the Ohm's law here, it's the product of the this current or to the resistance, yes. And the how to find the current here carried by a wire, we need to divide this delta V on resistance. Delta V, your potential difference in the American circuit of electricity system will be 120 volts. It's in numerator, and the resistance of the nichrome wire 8 ohm will be in the denominator, yes, and it will be equal to 15 ampere, yes. So actually we can find the power rating here, yes. What is the power of this special type of device of electric heater? So it will be the current squared on a resistance product, yes. The current squared we need to put inside the formula the numerical meanings of these values, and you will receive that its power will be 1.80 multiplying on 10 in the power of 3, yes, volt. Power of 3, 10 in the power of 3 could give you a kilo, yes, a special type of mathematical unit which uses the powers of 10, yes. Here is the power 10 in the power of 3, and you will receive that the power of the electrical heater, it's absolutely a normal electric heater that have the power of 1.8 kilowatt, yes, nearly 2 kilowatt. The AC current circuit, yes, we need to talking about the direct current circuit that containing capacitors, yes, resistance and capacitance circuits. The current may vary with time when you have the indirect current circuits containing capacitors. The current is still in the same direction, and RC circuit will contain a series combination of a resistor and a capacitor. That's why it's RC, yes. RC resistance, RC it's a capacitor, so it's a combination, RC circuit, combination of resistor and capacitor. The current may vary in time in this special circuit containing capacitors. Electrical safety. We need to talking about the electrical safety in these cars because it's very needable part of our classes. I don't know that you have already some noticeable rules or explanation of it about the electrical safety in your life, but I need to give you some information about that. Electric shock can result in fatal burns, actually, yes. The burns could be actually deathful, yes. It could be very fatal. Люди! Я пишу, у меня занятие. Electric shock can cause the muscles of vital organs, yes, so such as a heart, for example, yes. You when you have electric shock, it can actually cause the muscles of your special type of the organ. Some of them could be vital, yes. So it's extremely important for the life, yes, for the life existence, such as the heart. The malfunction, yes, malfunction could be used like electric shock, yes, and it could damage your muscles of vital organs actually. So the degree of damage will depend on the different type of the features of the current, the magnitude of the current, the length of the time it acts, the current it acts on your tissues of the body. It actually depends on the part of the body which is touched by the live wire. Yes, so live wire could differ from differ damage, could actually cause differ muscles malfunction. Yes, depends what exactly the muscle. If it's hard, it will be malfunction of the vital organ. If it's just arm, you could have the fatal burn of the arm, but it wasn't be so absolutely fatal. Yes, the part of the body in which the current exists in this part, in this time, in this point of time, if I could, yes. It depends what exactly happens, but it could happen very fast that you even noticed what exactly the part of the body, what happens, yes. Everything could be very fast in the some seconds, in the some periods of seconds. So we are going next, yes, about the effects of various currents. So 1 milliampere, M here, it's a milli. Yes, in the do you remember this table of the powers of 10? Yes, this is a 10 in the power of -3 milli. So 5 milliampere or less. This current can cause a sensation of the shock. Generally, little or no damage, but if you have some electrical devices like cardiostimulator, yes, this type of various counter currents like 1 milliampere or 10 milliampere, where you have muscles contrast, yes, and maybe unable to let go of a live wire, yes. So the something near difference between them in this diapason, in this range of the milliamperes, from 5 milliampere to 10 milliampere, it's generally little no damage, but some of these units of the ampere could be it's using like little damage in the electroshock devices which are using by police or something like that, but it's normally acting when you have the very strong healthy man, for example, with no problem with the heart system. Yes, but if you buying a shocker, yes, electrical shocker, please remember that some person could have actually cardiostimulator or problem with the heart system, yes. And in some period of time of these 4 acts of the this heart heart acting system, we have 4 tacts. Yes, we will talking about that when we will talk about the electrocardiogram. In sometimes the of this these 4 acts of the heart working system, we could actually damage heart. Damage act not heart muscles but the heart acting work. Yes, how it works. So damage this engine system, if I could say in this way. So it could cause heart attack actually. So the use of the shocker could cause in some special type of the heart diseases. Yes, the using of shocker could cause a special heart attack. Yes, sheer heart attack. Don't forget about that point. Yes, that's why it's only used by police in some countries, so they are the public. Sorry. So 10 more, the muscles contract to let go of a live wire. If you have 10 milliampere, if this current, if it passing through the body, it can be fatal. Yes. So some ampere, yes, it's something like fatal special of the amount of out of the current what could be fatal. It paralyzes the respiratory muscles and prevent breathing. Yes, this is damage. The damage point of the current, yes, for the human body. In some cases, current of 1 ampere can produce serious burns. Yes, actually. Sometimes this can be fatal burns. Yes, why it happens? Because of the thermal action, thermal energy, which is act on the skin, which is good resistor actually. Yes, skin, the under skin layers, some fat, human fat. Yeah, it resistors, and this is the active resistance. So they are, when the current going through them, that give us a temperature effect. So they have us the going out. Yes, the some like the extra going of temperature effect. So this thermal effect of going current through it give us the serious burn, and sometimes these burns could be fatal. It depends of the amount of the skin, area of the skin which is burns. Yes, what is the area of burn, it could be fatal. More than 50% of the body, it could be fatal. So no contact with live wires is considered safe if the voltage is greater than 24 volts. Yes, it's considered safe again if the voltage is greater than 24 volts. So no contact with live wires. We need to talking about the ground wire. In situation that show on the picture, the live wire has come into contact with the drill case. Yes, so we have the wall outlet. Here is some like American system, because we have the American cars of the physics for medical student from the Professor Mouridine. Yes, from Yemen University. And this situation, the live wire has come in the contact with the drill case. As a result, the person holding the drill, If you're holding two arms, yes, acts as a current path. The person will be at the current path to a ground, and this person receives an electric shock. Yes, ouch! It's painful. It's actually very painful, yes, because we have ground here, yes, and we have these 2 points of different potential. We have neutral line, yes, and we have the circuit breaker line here, circuit breaker inside the on the enter of the house. We have special type of the safety circuit breaker, and we have the line of the circuit with the 120 watts, and this current are going through this wall outlet. And when you put inside this live watt outlet your device, yes, the drill, for this example, when these joints of the drill have the bad insulation, the drill acts as a current path to the ground, and a person could receive an electric shock. The electrical equipment manufacturers use electrical cords that have a third wire, call it a ground, actually. Yes, we also have this ground third wire in our old Russian or Soviet uh, electric circuit. Yes, in our system, in our European system, we also have this third wire. It's the electrical equipment safety. Yes, this safety ground normally carries no current and is both grounded and connected to the appliance. Yes, if this line with the live wire is accidentally shorted to the casing, actually, the most of the current takes to the low resistance path through the appliance to the ground. So the current, like a river, trying to find some lowest resistance path, yes, to go, and it finds some way, yes. The most of the current takes the low resistance path through the appliance to the ground. Yes? So if it was not properly grounded, anyone in contact with the appliance could be shocked because the body produced a low resistance path to ground. Yes, we have some resistance of the skin and we have some resistance of the body, but it actually low in difference from the another outer space. Yes, so it will be the our body produces a low resistance path to the ground for the electric current. Please remember about that. Yes, in the situation here on the second B picture, the drill case remains at ground potential and no current exists in the person. Yes, because we have the ground, yes, neutral and ground. We have hot wire, we have neutral wire, and we have ground wire. Yes, so for the first time we have neutral, which is joined to ground, and the current takes the low resistance path through the person. Yes, uh, through the appliance, this appliance to the ground. In second part, in this situation, the drill case remains as a ground potential and no current exists in the person. In this low resistance path is the most lower is your wire. It's your ground wire. It's the more low resistance. That's why it's not going, it's not full. Yes, actually, the electricity, if I could say it that way. This is, the physicist is joking. Yes, it's a joke. It's something like special type of intellect. Yes. So the lowest path of the low resistance is the going through the ground wire. That's why we need this properly grounded wire. Anyone in contact, yes, is the appliance of the current. If it not properly grounded, everyone in contact with the appliance could be shocked because the body produces a low resistance path to ground. But if we have the third line, third wire outlet, yes, and we have the ground, it's the rule of safety. We have the ground wire, it's the lower way to the current going up to ground. Yes, ground fault interrupters, GFI. We have no here in the Ukraine, but this exactly interpretation. It's in another interpretation. But ground fault interrupters, it's a special power outlets. Yes, these three wire outlets. In the UK, in the USA, we have the special power outlet, use it in hazardous areas, and they're designed to protect people from electrical shock. The sensor current, it's less than 5 milliampere, leaking to ground actually. They quickly shuts off the current when above this level it's good leaking to ground. Yes, electricity within the body. Yes, and we need to talking about how electricity plays an important role in medicine. We know that there are two aspects of electricity and magnetism in medicine. First one, that electrical and magnetic effects generated inside the body actually. Yes, so we have some special type of electrical and magnetic effects generated inside the body. And also we have the applications of electricity and magnetism to the surface of the body in the some medicine equipment. Yes, so the electricity generated inside the body serves for the control and operation of the nerves, special tissues. Yes, nerves, muscles, and a special type of organs. The forces of the muscles are caused by the attraction and repulsion of electrical charges. Yes, we will work in this special type of the physical model, some simple physical model of process by the attraction and repulsion of electrical charges in our body. And the action of the brain is electrical, actually. Yes, we have some electrical potential signals to and from the flow of electrical currents. Yes, in some explanation, and we have the provement that the all nerve signals and to and from the flow of electrical currents. One means of obtaining information about muscles is the electrical activity actually. Yes, the electrical activity about the muscles. Yes, the transition of the action potential from the axon, for example, yeah, to the muscle caption. The potential difference between inside the cell. Yes, about the this membranal. Yes, membrana of the tissue, about the this natrium calcium transport, natrium calcium pump inside of the cells. We will talking about this in another lectures, but now general of the cell of the here, and we have the difference of potential plates of the conductor or something like electrodes system. We have this equal number. Yes, the we have when we have to look on the this savanna of the little part of this barrier, very thin barrier with the two cells actually of the lipids, thick, very little barrier between the inner space and outer space of our cell. Yes, so here is a cell on the picture, some simple cell, and we have very simple explanation picture of it. This barrier of the outer membrane of the cell and some organ inside it, and we have this different type of the cells here. Charges. We need to find the potential difference outside the cell. So you have pluses, F minuses, different sign of the charges. Yes, or in inner membrane, the surface of the membrane. Yes, this net separation charges across membrane here. Tiny, very tiny border between these two between potential difference between inside and outside the cell, and also have this equal number of pluses in ACF, in space of the cell. Yes, we have the result of potential will be minus 0.07 volts. Yeah, this membrane, it's called membrane. The biomembrane potential. Yes, spatial. So we have RMP equal to this separation of the charge across membrane, difference of potential. Then when we put what happens, we actually spike of potential here, of depolarization. In the potential it's more, it will be the sum overshoots. Then we have the repolarization when the little bit less and potential there on the graph. Yes, and after some period of time we have after the process of polarization we have potential of after hyperpolarization. So something like what about more in the Levy physiology, the 6th edition. Yes, they explain what the and this process of the organic net negative charges and net 3 and chlor. Yes, on the cell membrane, difference between the actually absolutely differ inner and outer space. After we have the natrium chlorium solution in water and ions of natrium plus light minus outside the cells, and this little tiny cell membrane defects of organic anions with the calcium plus it's a net negative charge. Yes, that's why we have this different cell membrane on the biomembrane. But in culture, electromyography, EMG. Yes, what is that? Electromyography recording electric activity produced at rest and during contractions. So the technique, it's used for investigation of various neurological and determine the site and duration of action potential plants. The nerve conduction velocity can be determined using EMG machine. Yes, muscles action potential pick it up by electrodes. Place it near the surface of the interest. Yes, there are different types of lace, needle, and discs electrodes can be recorded by applying stimuli to with surface electrodes and observing the contraction of the muscles. One nerve supply here is the 100-300 muscle fiber, which is make up a motor unit, something like that. So when a nerve its charge of muscles fibers are activated. So the EMG electrodes, here is the picture. Yes, you have the different colors to mistake them. The EMG electrodes records the electrical activity from so single muscle cell are usually not monitored in EMG examination. Yes, because it is difficult to isolate a single fiber. Yes, and we have the electrical here about the stimulator to the muscles. Yes, this hemostimulator of device, and it's time reference for C. Yes, and we have the this ground here to not getting shocked. Yes, pain shock to the patient by electricity shock. And we have here two pick ups which join to amplifier. Yes, we have transformation of the signal which is going up from the electrode, and then we receive this after the transformation of the signal, we receive exactly CRT signal system, yeah, to nearly 1 millivolt, 1 milli, 10 and the power of -3 volts. This special type of action with the time. So we find the shape of the action potential nearly milliseconds, 10 in the power of -3 of seconds, with the going of time. We have this space, and the latency of it is the 6 milliseconds CRT. Form shape of electric potential of the muscles. Yes, of this EMG allography. Yes, electrical signal from the heart is the rhythmical action which is controlled by an electrical signal, initiated spontaneous stimulation of the special muscle cells located in the right atrium. So this rhythmical action of the by electrical signal, they are initiated by stimulation of the special muscles cells. It's located in the right atrium. The cells make up the senatorial SA node, or the senatorial node fires at regular intervals. Yes, the electrical signal from the initiate the depolarization muscles of both atria, causing the atria to contrast and pump blood into the ventricles. Yes, so this electrical signal from this senatorial node initiates the special type of the process, depolarization. Yes, different polarization of the nerves and the muscles of both these atria to contrast and pump blood into the ventricles. Repolarization atria follows special type of the electrical signals, which is change the sign of polarization. Yes, the electrical signal then to the atrioventricular node AV. Yes, atrioventricular AV, we will call it AV, which change the depolarization of the ventricles. It causes them to contrast and force into the pulmonary and general circulations. Yes, the ventricular muscles then repolarize, and repolarize, and the sequence begins again. Yes, this again and again. It's a normal work of your heart. Yes. Nerves and the muscles of the heart can be regarded as sources of electricity in closed electrical conductor. Yes. Potential distribution of the chest here. Yes. On the picture at the moment when the ventricles half depolarize. Electrodes located at ABC points. They would indicate the potential at the electrical cardiogram. Yes, electrical signal from the heart of 3-point potential located point ABC. They would indicate that moment. Yes, some. So we need to talking about this 3 potential. Yes, something like that. What is your picture of your equipotential lines here? Yeah, and here is that your specific action actually of the current flow here. Yes, and we would need to talking about the this special type of the difference of potential inside the system. If here is our equipotential line, we will think about an electric dipole. It's the model of Eindhoven. Yes, it's the special type of the of our heart, something cylindrical like a heart, or like electrical dipole. Yes, so it's of the heart as an electric dipole. We need to talking about the basic principles of electronic dipole. Heart will be as dipole. The myocardium is charged negatively. Yes, it's the minus. Yes, it's somewhere here, and here is the yes, another place where is electric dipole. It's produced when negative charge. I remember you that we have charged points with the positive and negative charge are separated from each other for special type of the distance, printed like a vector. Yes, between positive and negative charge, and with dipole. Yes, electric vector of the heart, integral electric vector of the heart. It will be your dipole, which is the product of the this Q. Yes, and this this special type of the distance point of medium. Yes, it's your special type of the distance between these two charged points. Yes, the shoulder of the dipole. The electrical that we measure in one of the is merely the instantaneous projection of the electric dipole vector for a particular direction. Yes, so in direction we have space electric dipole vector. As the vector changes with the time, so does project potential. So we have these projections of the body. Yes, we have some planes. It transfers human body and this special type of sagittal plane. So sagittal plane, which is divided two parts of the human body. And the of electrocardiographic planes, when we're talking about vector RA, yes, electric dipole vector, which is from minus to plus, so from the upper side of the heart to the down side. The LA, RL, and LL, they will be include locations on the right and left arm. Yes, it will be left arm, right arm, yes, right leg and left leg. Yes, this is special locations vector. Yes, and the way from the it's sometime positive and negative. The sign of the water depends upon the direction of the electric dipole and position of the electric. So the electrocardiogram potential produced by the heart will be spread to the surface of the electrodes placed there. The process of potentials is known as the potentials are small, so they are required to be electrically amplified before they are loaded. Yes, on the figure. How much time is it? Do we oh my god, yes, so we are our time almost up. Okay, so the recording of figure that is showing us typical electrocardiogram. The potential P represents as the attraction and contraction. The QRC, polarization and contraction atrial. The QRC, yes, complex on the graph indicates depolarization. The ventricle contraction between CS represent the ventricle here, and then cycle of the EKG, HCG is going again. Again, we have P point, atrial depolarization and contraction. Then we have the QRS here. Complex indicates the ventricle depolarization, and T we have ventricle contraction, then the ventricular repolarization. Yes. And time measured in second. Figure here in electrocardiogram, it's for a normal subject. Yes, here 6 of them for a normal subject. Yes, they work normally properly, and 1 second it's your calibration. Yes, what happens in one part of the cycle, and the highest variation in voltage it's 1 millivolt, 10 in the power of -3 volt. It's shows on a picture what is a calibrated electrocardiogram. Yes, it's and the different and graph. Yes, maybe another picture of another point. We need to talking about more the programs. So that's all for this time. You could be free action.